Hi, my name is Brian Jackson. I'm a faculty member in the physics department at Boise State University. I'd like to talk to you about my group's work using small-scale meteorological networks to probe boundary layer processes. One of the most important boundary layer processes on Mars are dust devils. This is a series of images collected by the MSL lander from a few years ago. Dust devils loft as much or most of the dust into the Martian atmosphere, and so they play an important role in the dust cycle. Dust drives warming in the Martian atmosphere, and so dust devils are an important part of the Martian climate. We don't really understand exactly how they work, but we do understand their structures in sort of broad strokes. This cartoon illustrates those structures in terms of the wind profiles and the pressure structure. Wind speeds for dust devils on Mars are typically tens of meters. And because dust devils represent dusty convective vortices, they have small pressure dips at the centers. We can measure the winds and pressures induced by dust devils on Mars using landed instrumentation. So here, for example, the InSight lander has pressure and wind sensors. Here in the bottom panel, I'm showing the pressure in blue and wind speed in orange during a vortex encounter. And so from measurements like this, we can probe the interior structures of these Martian vortices. And therefrom, we can, in principle, infer how much dust these vortices are contributing to the Martian dust cycle. But unfortunately, an encounter like this doesn't actually tell us what the encounter geometry looked like. So for instance, we could have passed directly through the center of the vortex, in which case we're measuring the intrinsic properties of this vortex. Or we could have passed through the vortex some distance from the center, in which case we're going to underestimate the pressure and wind speed excursions associated with that vortex, and therefore it will be difficult to understand how much dust is actually being lofted, if any at all. To try to address this degeneracy between the intrinsic properties of a vortex and the encounter geometries, previous studies have deployed networks of meteorological sensors on the surface of the Earth. And so here, for example, is a series of images from the study led by Ralph Lorenz in 2015. For this study, they deployed a network of barometric and sensors and pyrometers on the desert at the La Jornada Range there in New Mexico. They deployed that line of sensors in a direction roughly perpendicular to the prevailing wind direction and collected a really lovely data set. Here I'm showing data from a specific vortex encounter as seen by several instruments in the network. So here on the left column, I've got pressure time series, and on the right column, I've got that solar flux measurement. And so you can see there's a dip in both of these time series from all of the instruments, indicating a vortex encounter, in this case, a dusty vortex, a dust devil. And so we can use the relative positions of these sensors and the time series collected to work out the encounter geometry and then therefrom determine the actual properties of the vortex and the amount of dust being lofted. And so we're following up on this earlier study. In this case, we're deploying a square grid of sensors on a field site known for dust devil activity in southeastern Oregon. This is the Alvor Desert. The instruments we're deploying are kestrels. Here's one of the kestrels we deployed. So these are instruments that measure pressure, wind speed, wind direction, temperature, a lot of the sort of meteorological parameters that you want to see when you're trying to understand what's going on here with these vortices. And so what I'm going to show you next is an illustration, an animation of a boundary layer structure actually passing through the network. So here we've got latitude north-south on the y-axis, longitude east-west on the x-axis, and then each of the red circles represents one of our instruments. The wind velocity vector seen by that instrument will be indicated with the arrows, and then a negative pressure excursion will be indicated by the size of the red circle. So as that negative pressure excursion passes through, the red circle will get larger. And what you'll see here is a low pressure structure pass through the network from south to north. Okay, there's that structure just blowing gently through our network. And let me run it again for you so you can see it. And so by correlating the time series between these different instruments, we can actually work out the structure of this feature from the sensors. We can also deploy alongside a dust sensor. So here's one of the dust sensors that we're using. Right here, it's actually duct taped to the tripod that we use for these kestrels. And we can see a clear spike in the dust during an encounter with a dust devil. You can see that basically the dust goes up and then comes back down during that encounter. And so these measurements give us some hope that we can actually use these small-scale networks to probe boundary layer structures. This is a really important proof of concept. Dust devils and vortices on the Earth and Mars produce these very distinctive and measurable signals that we can actually probe with these small-scale networks. And hopefully we'll be able to work out the relationships between a vortex's properties and the amount of dust lofted here on the Earth, and then extrapolate from that to Mars and understand better how the dust cycle works there. With that, I'd like to thank you very much.